Hello, my name is Hunter, and this is Lab M2B, the simplification of Boolean functions. In this lab, we will simplify a Boolean function and then build it in order to demonstrate the relationship between a Boolean function, a truth table, a logic diagram, and the output values. The equipment we used in this lab were various jumper wires, one breadboard, a 5-volt power source, an a 74LS04 NOT gate, a 74LS32 OR gate, and a LED light. This is my NOT gate. This is my OR gate. This lab consists of the design, schematic, and testing of the circuit. To design the circuit, we must first simplify the given Boolean function. This top row is my Boolean function that I was given. The first step we take in simplifying this is using De Morgan's law. The inverse of everything inside a parenthesis, if they're being added together, is to multiply them times each other and take the inverse of each variable. So x became x prime, y became y prime, and z prime became z. And instead of adding them, we multiplied them. And then we use the absorption to change this bit here, y prime times z plus y, into x prime times z plus y plus z prime, which equals this, x prime times z plus z prime plus y. And we will use absorption again to get our final simplified equation, x prime plus y plus z prime. I will now be walking through and testing the circuit. Our yellow wire going in here is our 5 volts coming from the 5-volt source. The yellow wires are the VCCs for both gates. There you go into the positive node with the 5 volts. Black is grounded, that's our ground wire, and black wires were used to ground the gates as well. Okay, so our orange wires are the inputs x and z. Orange is x and z because they are the inputs that will be getting inverted. So you can see right here, well, maybe I'll use this one, it's closer. We can say this is z. Z goes into the inverter, and the output is the white. So the white right here is z prime. And the other orange wire goes into here. And the output is this white wire right here, and that is x prime. And both z prime and x prime go into the OR gate, and they are being added to each other. And this blue wire is the output, and the output goes in over here and is being added to our y input, which is indicated by this white wire. And then the output of both the sum of x prime and z prime and y is indicated by whether this LED light is on or off. Okay. So by default, I have the LED being turned off because x and z are both plugged into the 5-volt voltage source, and y is grounded. But since x and z are being inverted, they are both outputting 0. So it's 0 and 0 being added together, plus y, which is also equal to 0, which is why the LED is turned off. You can see it is plugged into the 5-volt source and it is on. But if I were to, let's say, change x, so take x from the 5-volt source and plug it into ground, it will now turn the LED on because x is 0, right? This orange wire right here, 0, and it's being inverted and then turned into 1. So it's 1 plus 0, because z is still 0, plus y, and y is 0. So 1 plus 0 plus 0 is 1, which turns the LED on. Now if I were to plug this back into 1, and I would to turn z on, by plugging that into ground, z is now being inverted from 0 to 1, which will turn on the LED. Now putting that back, if we were to take y from ground to the voltage source, it will turn the LED on because x and z are both, well, x prime and z prime are both 0, and they are being added to y, and y is 1. 0 plus 0 plus 1 equals 1. Now if I were to plug y into 0, or y into the 5-volt source, and then x into ground, oops, I have that set up wrong, x into ground, it makes no difference. Same with z. So now all of the variables being added together are 1, x prime is 1, z prime is 1, y is 1, which will output 1. I will now be going over our procedures. First, we simplify the given Boolean expression, and then we derive the truth tables for both the given and the simplified Boolean expressions. Using a simulation software, we will then create and simulate the circuits for both the given and the simplified Boolean expressions, and we will check if the outputs correspond to the respective truth tables. Once we are in the lab, we will construct a simplified circuit with an LED indicating the output. And then we will test the circuit by applying voltages into each input that correspond to the truth table and compare the measure outputs to their expected outputs. For the truth tables, I have the given expression, which was x plus y plus z prime, or z naught, all inversed, plus y plus z prime. And we see that the only time that the output was not on was when x and z were 1 and y was 0. And this was the only time where the output is 0. For the simplified expression, we see the same thing. The only time that the output is 0 is when x and z are 1 and y is 0. For both expressions, the output will be 1 for every other input. If x is 0, or if z is 0, or any other combination of inputs, the output will be 1. But if x and z are equal to 1 and y is equal to 0, then the output of the entire expression will be 0. I will now be showing you the simulations, or the schematics, using multisim. So this first one, this big, very complicated schematic, is the given equation. I used a switch for each input. Top one is x, this middle one is y, and this bottom one is z. And since the expression is x plus y plus z prime, or at least the first bit of the expression, we have x and y not being inversed, with z being inversed. And then we add up x, y, and z prime. We do this by adding x and y here, and then x, y, and z prime here. And then we put it through a NOT gate, and then we add that to y, and then we add that to z prime. And that gives us our output, which should be, it should only be 0 if x and z are equal to 1 and y is equal to 0. We can test that right now, and this seems to be true because x, the switch is closed, same with z, so they are going to be 1, and y is open, so its input is going to be 0. And if we were to change this at all, let's say let's open x, the light turns on. Let's close x, and let's open z, the light is on. Let's close both of them, and let's close y, the light turns on. And this is any combination. This is the case. Okay. Now let's look at the simplified circuit, which is x prime plus y plus z prime. This is x, y, and this is z. Since we have x naught and z naught, we have to put them through a NOT gate. And then we will be adding x prime, or x naught, z naught, and y. So here we add x naught and y, and here we add x naught, y, and z naught. And this should be the same as our truth tables and as the last simulation. If x and z are both equal to 1 and y is equal to 0, then this should be off. And for every other input, the light should be on. So here we see the light is off. And if we were to change anything, let's open up x, turns on, let's close x, let's open up z, it's on. Any other change we make, it will turn the light on. The only way for the light to be off in both of these circuits is if x and z are equal to 1 and y is equal to 0. In conclusion, I think I have met the given objectives because I was able to simplify the expression from this into x naught plus y plus z naught. It went from many components to just 3 components. I was also able to simulate the given and the simplified circuits with corresponding inputs and outputs, meaning that if the inputs here match the inputs here, then the output here will match the output here. And I was also able to build the simplified circuit in the lab and have the input and output of that simulated circuit correspond to the truth tables and the simulated simplified circuit. I did not run into many problems while doing this lab. I ran into a few while building the circuit, such as not having the OR and NOT gates connected correctly, but I was able to quickly resolve these issues. And I think to better improve my lab, I probably could have made my circuit easier to read and look at because I had some wires crossing each other, making it hard to read. But there wasn't much I could find that I could do to resolve that issue without using more wires. And I could have also have color coded the wires better, but with the wires I had at hand, I found it harder to color code it more clearly than I